Well, thank you, Fred, and I want to thank you for including me here. I've actually spoken at a number of precision medicine, personalized medicine, precision health conferences, and I must say this has been incredibly well organized and great talk, so I'm really honored and privileged to be here. It's also amazing how similar some of the concepts I'm going to talk about will reflect very much what Jeff Loeb was saying before. In fact, he kind of has taken this bottom-up approach, starting with a specific problem and looking at the data and trying to build a system. I'm going to try and take the data we already have and a top-down approach to kind of think about how this all can be put together in a hospital system. I'm going to start out by thinking about what is personalized medicine. And I'm going to give you a couple examples. And I'm going to start out with some cancer. So this patient, a woman in her early 50s, young now from my standpoint, unfortunately developed a lung tumor. And this particular lung tumor, when it was diagnosed, was actually already metastatic to the brain. It also was a very important time in history. This was 2004. 2004 was the year that the epidermal growth factor receptor was identified and activating mutations were identified, that there were drugs that could target those, turn off that pathway, and impede the growth of those cancers. Now, before 2004, a patient who presented with a metastatic lung cancer had a chance of survival for even a year and a half of less than 1%. But as you can see from this, she actually lives many years. She ended up living about 10 years. And it was because we were able to identify a specific mutation in her cancer, very personalized. Other cancers don't have this one. This was for her. And we could treat it with a specific drug. Well, it turned out a couple years later, her cancer started coming back. And we then went back into her cancer and found a different mutation, a resistance mutation. But by that time, a different drug had been identified. And we could put her on the right protocol, and she lived another about 6 years after this. So the important thing here is that we can use personalized medicine to treat an individual's tumor with the right drug. We can get them on the right treatment protocol. Here's another, I think, really important example of something else we can do looking at personalized medicine. And this is another very young individual, 42-year-old, who was diagnosed with what was called at an outside institution an atypical small cell carcinoma of the lung. Now, these tumors are notoriously difficult to treat, but usually, when you put them on the right treatment, they have a very good response initially, and then they recur. This individual didn't respond at all. Was sent over to our cancer center at the Dana-Farber. We then looked at the molecular characteristics of this tumor and identified a specific translocation that changed the diagnosis. This wasn't a small cell carcinoma of the lung. It was a Ewing's carcinoma. We put that person on a Ewing's protocol, and they did actually very well on that. So again, now, instead of getting on the right treatment, it's actually used for making the right diagnosis. I'm going to come back to these points. Just very quickly, how do we do this? We have a deep sequencing panel. It's a 446-gene panel that we look at using next-generation sequencing. We've now done it on 25,000 tumors, so we have a very good experience with this. But what I really want to point out on this slide is that the data we get is in the upper left corner, all those bright lights, those spots. And if we gave that data to a clinician, it's worthless. There's no clinician that could actually take that data and use it in a daily practice. So we have to convert that data into information. The information is that those bright dots reflect A, C, T, and Gs, the base codes of DNA. And once we have those and the order of them, we can actually convert that information. We now have information of what those strings of DNA are. We can then map them onto genes in the human genome. And that's at the bottom, all those 446 genes we look at. And now it becomes knowledge, because we know when there's mutations in any one of those, that can have an effect on the cancer and change our diagnostics, our prognostics, our treatment stratification. So I'm going to come back to this concept because we need to think about how you take data, convert it to knowledge, to information, and then to knowledge that can be used by the healthcare system. What we know from doing these 25,000 cases is that it works. We can actually get results over 95% of the time. We find common things, common CNVs, copy number variants, commonly. We also find things that we don't always expect. So, for example, we've identified some Pol E mutations in certain types of cancers, such as endometrial carcinomas, that are very highly mutated, and we know that they have a better prognosis, and we treat them differently now. Those are not common in endometrial cancers, but when we find it, we treat them differently. And we find unexpected things. We find things that are, an ERB2 and a mutation, which is targetable as well in an ovarian cancer, and we actually treat it that way. Now, very quickly, this is great for solid tumors. It's not adequate for hematologic or liquid tumors. And so we developed something called a rapid heme panel. I'm not going to go through the details. We can turn this around in just a couple days. It's actually effective for our patients. And we also have identified things. And the key point here is that this was a young individual, 18 years old, who had a rapidly progressive acute leukemia, who we found a notch mutation and got onto a treatment protocol. Okay, so this person actually was not doing well, was advancing very quickly. We found a specific mutation. They went on to a protocol that helped them individually. Again, this is personalized. What we know now is that when you do this kind of work in cancer, that we make better diagnoses, we do better job of treatment stratification, we get better patients on the right protocols, we do a better job of prognostication for those patients. We've also discovered new biomarkers and have been able to do more work with it. But, these treatments in general tend to be less toxic. Patients do better on them. There's actually data coming out that even though they can be incredibly expensive, $100,000 a year or more, they're actually less expensive than traditional chemotherapy because the patients spend less time going to the ER. One ER visit can be $15,000. You don't go 2 or 3 times in a year, you save a lot of money. Shorter hospital stays. These are all things that decrease the cost of healthcare. And this is just to remind me, it's not just for cancer. This was a child that we had developed a next-generation sequencing test to identify silent translocations that cannot be detected by traditional methodologies, and allowed this family to be able to identify when they had a normal child. They had previously had an abnormal child. So we can do this for germline as well as somatic mutations. Now, all of this is great, but it's extraordinarily challenging to a clinician. Clinicians, and there's very good data coming out of ARUP and other places, can use about 5 pieces of data each time they see a patient. So you go in for your annual review, your annual exam. A clinician may order a CBC and a panel 7, a metabolic panel, a lipid profile. They've got 30 parameters that they're going to get, and they can use 5 of them. Think about when we present them with a whole genome with 50,000 variants in it. There's no way. We have to synthesize that and help them use that data more effectively. So I'm going to take a little digression here to kind of give you the concept of what I think about how we can actually use this data more effectively. And it comes from maps. So those of you who are Tolkien fans, you probably recognize this is Middle-earth. And maps are fantastic. They tell you where to go, how you get from one place to another. But they're static. They won't tell you where the orcs are hiding to sabotage your trip to destroy that evil ring. And so what has evolved are dynamic maps, and that's Google. So in Google, you have a database that is basically all the roads to get from one place to another. But you can also use Google Maps to understand where traffic is. So you can know which way to go to avoid being able to get stuck in traffic jams. This is Boston. You can see there's hardly any red on it, so that means it was about 2 in the morning, because otherwise it's always red. But there are ways to do it. And you can use it to actually plan entire trips. So you can plan where you're going to stay. You can plan hotels. You can plan what gas stops, where you want to eat. Everything can be planned by just doing a simple search, just by typing in the search line to Google. And you can even link that to Google Earth. So you can see each turn you want to make so that you have a visualization of what's going to happen or where you're going to turn so you don't miss a turn. Now, the beauty of Google, what they've done is they've actually created relational databases. So all those things I just stepped you through, the map with the traffic, with the Google Earth, with the hotels, all of that is not in a single database. Those are each a different layer of databases. And each of those databases are relational to each other. So when you type something into the Google headline, into the search engine, it's going to interrogate vertically through each one of those databases. But it's not going to go to each one. It's only going to go to those that you ask it for. And in doing so, you can get all that information. And that's the concept that we need to think about for healthcare. And that's going to look something like this, where we take phenotypes, we take the signs and symptoms that very astute clinicians record and put that into a layer. And we take another layer that includes the genome, much of what we've been talking about. The microbiome would be another layer. The epigenome. The exposome. What drugs have you taken? What other sun exposure, other exposures that you've had? Each of these can be put into a different database, but relational to each other, so they can be interrogated vertically through each one of those layers. And this gives you the opportunity to really dig down deep into the data and use it more effectively, just like we do with Google. So what does that look like in healthcare? How do we do this? Well, here's where we are today, for the most part, and I'll give you some caveats. But today, what we do is a busy clinician is going to see a patient. They're going to order some labs. Now, I just put labs up there because I'm a pathologist, but that could be radiology exams. It can be any number of things, EKGs, EEGs, EMGs, all these different things that they're going to get data on. And they're going to be asked to synthesize all that data to make a decision on what should be done with that patient for their care. Remember, they order all these things. They can use 5 at a time. And what really needs to happen is we need to start building algorithms that interrogate different databases to be able to give them more information. Let me give you an example of a very simple algorithm. When a nephrologist wants to know renal function, they don't just look at a creatinine and a BUN. They look at something called the GFR, glomerular filtration rate. It basically looks at how each glomerulus in the kidney is functioning. Well, that's a calculation. We collect 24 hours of urine, we look at creatinines, we look at a number of different things, and we can measure it. It's a simple algorithm just from the laboratory data. Here's one that's a little more complex. All of that information I told you before, where we were sequencing those tumors, requires a huge amount of data that's outside of our laboratory. We go into external databases, we go into the literature, we pull all of that together to build a report that has tiers of what each of the different results are in the particular tumor so that we can give our clinicians information. Here's tier 1. Those are targetable, druggable targets. Tier 2, these are prognostic. There are no current drugs that can be used for them. So we can give them very specific information about each of those pieces of data based on everything in the literature, based on other tumors, how they've responded, everything we need to know. Giving that to the clinician gives them an opportunity to actually use this massive amount of data. And it truly is massive amounts when we sequence tumors. Well, what we really need to start thinking about is how do we integrate all of that? How do we take what that clinician sees, that phenotyping that they do, along with radiology exams and pathology data? There's a huge amount of data. At Partners Healthcare, which includes the Brigham and Women's Hospital, my hospital, the Mass General, and a bunch of community hospitals, we just went into Epic about 2 years ago. We converted data for 5 years in real time. Older than 5 years is archived. The second most common data source was radiology. We had to convert 14 million data points or exam results into our new record. Pathology was the biggest, 500 million. 500 million reports for 5 years. And one report could be an entire genome. So that's what we had to work with, that we need to synthesize to be able to provide to our caregivers. So what does this look like? What does it mean? Well, let me give you a very concrete example. This was work done by John Higgins, who trained in our department. He basically took the CBC. The CBC has this 9, 10, 11 different parameters. Let's focus on those at the top. And he took it on 10,000 of them, all on patients with iron deficiency anemia. They are known patients with iron deficiency anemia. He actually gave all these results to 5 hematologists and said, what can you tell me about those data? And they could tell you if the patient was anemic or not. He then trended the data. You can see that in the far left lower corner. And they said, now what can you tell me? And they could tell you when that patient was anemic or not. He then went into the literature, and he said, well, what's the shape of a red blood cell, biconcave? What's the average life of a red blood cell, 120 days? And what do each one of those parameters have to do with those two things? And what's happened with those patients when those things change? And he built some mathematical models that were actually self-learning based on Bayesian principles. So this is not a neural network type. And he was able to predict with greater than 95%, 96% sensitivity, 88% specificity, who in that population, there were 2,000 patients, 10,000 results, who in that population of patients was going to be anemic in 60 days. So now, all of a sudden, what we can tell our clinicians is, this patient you need to pay attention to. Here's the patient you need to spend your time with, give them iron, give them a transfusion, give them EPO, however you're going to treat them, so that they don't become anemic, they don't have the complications of anemia, they don't end up in the hospital, which we all know is a bad place to be, and they don't end up with, and they stay healthy and productive. They're at work. They're not missing days of work. At the same time, about 80% of the patients, we could say, you know what? You're fine. You don't need to take that iron that's going to cause constipation, abdominal pains, and all these other things. And we'll check you again, and we'll see if in 2 months you need to be looked at. But it frees up the clinician to focus on that very small group of patients that need to be observed and looked at, and not have to pay time and attention to those that are going to be fine for the next couple months. So this is the idea of what we want to do. And each time we see that patient, each time we get more data, each time that clinician sees that patient, it becomes a dynamic system so that you get more and more information that feeds back into this so that the clinician can get more information of how to manage, how to take care of their patients. Whether it's iron deficiency anemia, whether it's cancer, whatever it is, we look at them dynamically over time. Now, to do this, we've had to build an infrastructure. That infrastructure has 4 pillars. In the center, there's a pillar that says hardware and software. This is basically the people that are going to collect the data. They're going to organize the data because we have to structure it into those different domains, in those different layers, so that we can interrogate it. It's one of the biggest problems in healthcare, is that our data is completely unstructured. We still have this problem. I'm not saying we've solved it, but we've gone a long way in making this more accessible, all that data accessible, at least for our system. But it's how do you store the data, retrieve the data, curate the data. That's what's in the hardware. And then there's the bioinformaticists, the people who are actually building the algorithms to test these hypotheses and do the actual work that understands how to use that data. And then on your far right are the, I call it my factcheck.com. These are the folks that are going to basically do the statistics to make sure. We can build an algorithm that'll tell us almost anything. We want to make sure that it's relevant to our patients. So we go through and we've done that. And then the final one on the far left is a knowledge pipeline. How do you make this actionable? How do you make this actually work in a healthcare system to get it back into our busy clinicians' hands? And that's the last part we're working on. And so this is what it now looks like, and there's a couple publications that I've written on how this works. Basically, starting in the upper left, you have to take external databases, the literature, genomic databases, all kinds of different databases, proteomic databases, metabolomic databases, these all exist. And you combine that with your internal data, pharmacy data. What drugs has this patient taken? Clinical phenotyping, and all that other types of testing that we've referred to. And then you need to compile it and structure it, whether that's in a cloud, that's my little silly drawing of a cloud, or in a cluster, or in a server farm, however that's organized. Now you have the data. Remember, those were those bright dots that we had. That's only data. Nothing can be used at this time by a clinician. We have to convert that into information. And that information is what we do through informatics. That was that second group after the structure of the database. And then we need to do the testing to make sure it's real, the actionable information. And that's where we have test those models, and that becomes knowledge. We now know that a mutation in KRAS is associated with adenocarcinoma of the lung, particularly from smokers. And what does that mean, and how do we use that data? So we have that knowledge now. And the last thing then is, how do we get it in the hands of physicians, the laboratories, the healthcare systems, because we're talking about managing populations now, not just individuals. And also individuals, because now everyone wants to see their data. They want to see what comes out, and we want to give it to them. And we do that through this integrated reporting, like I described for the cancers and for the hematology example, but also for, through decision support that we provide for our clinicians. And I'm going to run out of time, so I'm not going to talk about a couple other examples. We've been working on I was going to tell you about some work we're doing in pulmonary precision medicine that has helped us better understand who to transplant and who not. And also a C. difficile project where we've been able, using clinical studies, computational models, and the microbiome work, identify actually 2 organisms that we believe now and we have in trials that given to a patient will actually prevent all C. difficile. We think we can give these 2 organisms. But we are also, and I'm going to end on this one, using deep learning to take information, and this is an example from Kun Yu, who's now in our department, where he can take features of tumors by histology. At the bottom on your left is adenocarcinoma, on the right is squamous cell carcinoma. He's built an algorithm that actually better predicts, in those bottom 2 graphs, better stratifies patients that are going to progress and not progress than either staging or are tumor grading by histopathology. And what's really exciting about this algorithm, which uses 9,781 features in a CNN, a convolutional neural network, when we combine it with molecular data and with patient outcome data in these different layers to interrogate it, that's how we're doing this, we actually can use the same algorithm now for brain tumors. And it's showing the same type of stratification. So it's becoming generic in terms of our ability to do these kinds of deep learning that allow us to better make predictions and better care for our patients. So I'll end here by saying that what can be delivered? We need to leverage the data we have, our electronic medical records, and all these siloed data that exist throughout our healthcare systems. And ours is as bad as everybody else's. I'm sure everybody has faced these problems. We need to bring those together. I do think that this is going to provide higher quality healthcare. You can see where it can already do better prediction modeling. It can provide better diagnoses. It can provide better treatment stratification for our patients. It will provide not just for individuals, but for populations of patients. And it will be something that will really support the mission of healthcare by caring for everybody at a lower cost, which we will have to do as well. So I will end. This is a big team of people. I don't even have everyone on here, but this is the main groups that are involved. Thank you.